This diagram shows three rays of light which are traveling towards the right. There's one here, there's one here, and there's one here. And these three rays are incident on this concave mirror and reflect from it. We can't see where the three incident rays have come from, but presumably they've come from a very distant object located on the optical axis of the mirror. Because these three rays are parallel to the optical axis, or at least very close to being parallel to it, they get reflected through the focal point, and so we get an image of the distant object here. Let's see what happens though if the very distant object is not on the optical axis, but instead at a point somewhere above it. The rays coming from that distant object that actually managed to hit the mirror will still be essentially parallel to each other, but not parallel to the optical axis. And we see that the reflected rays no longer form an image at the focal point, but instead at this location, which is vertically below it. In fact, it doesn't matter what angle the incident rays make with the optical axis. As long as that angle is small, they will be reflected through a point somewhere along this vertical line, which is a cross-sectional view through what we call the focal plane. The focal point lies on the focal plane, and the focal plane is perpendicular to the optical axis. If we put the very distant object below the optical axis instead, then we get an image of it which is still on the focal plane, but which is now vertically above the focal point. If we have a convex mirror instead, then a similar thing happens. Very distant objects located on the optical axis will have virtual images that are at the focal point, which is of course now behind the mirror, and distant objects that are not on the optical axis will have images that are either above or below the focal point instead. But again, all these images of distant objects will be on the focal plane of the mirror, which is perpendicular to the optical axis and which includes the focal point. Let's have a look at this question now, which has essentially given us three parallel rays of light, which presumably have come from a distant object, and are incident on this concave mirror. And basically what we want to do is to figure out how these three incident rays are going to reflect and so locate the image that they form. Now, in general, figuring out how they reflect looks in this case pretty tough. It looks like we might actually have to get out a protractor and measure up some angles of incidence and reflection. But actually, if we look at this middle ray very closely, I can see that whoever drew this diagram has been very kind and made that middle ray hit the mirror at its vertex. And we know what that is going to do. So we don't need to use a protractor there. So let's go, we'll extend this middle ray up to the vertex. And if we label up the angle of incidence as being theta, then we know that the reflected ray has got to make that same angle with the optical axis. Now we can achieve that just by noting that, well, the incident ray was 5 squares above the optical axis here. So that means that the reflected ray is going to have to be 5 squares below the optical axis there. So let's go 1, 2, 3, 4, 5 squares below the optical axis and put our ruler in the right spot. Now we can draw up the reflected version of the middle ray like this. And just for completeness, let's label up the angle of reflection as being theta. Okay, so that's one ray done. Now we also know that because these three rays are parallel to each other, they are going to form an image on the focal plane. The focal plane passes through the focal point and is perpendicular to the optical axis. So it would be enormously helpful to have the focal point. So let's figure out where the center of curvature is, because we know that the focal point is going to be halfway between the vertex and the center of curvature. So that center of curvature there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 squares to the left of the vertex. So if we were to go to the point which is 7 squares to the left of the vertex, 1, 2, 3, 4, 5, 6, 7, That's where the focal point has to be. The focal plane, of course, passes through that focal point. So we can represent the focal plane by a line like this. We know that the image of this distant object is going to be somewhere on the focal plane. So all we have to do to locate the image point is look at where that reflected ray goes through the focal plane, which is this point here. So the other two rays, well, they're going to reflect back through that point. So to draw those on, all we need to do is extend them up to the mirror and then make sure that they're reflected. The reflected rays pass through that image point. So this one is going to do something like this. And the other ray is going to do something like this. And there we go. We've completed the ray diagram and located the image. Let's have a look at this scenario now, which is very similar to the one we just looked at, but instead of having a concave mirror, we have a convex mirror. So again, we've been given three parallel rays of light, which have presumably come from a distant object above the optical axis, and they're incident on the mirror. And we just want to know how these rays are going to reflect, and so where the image that they form is going to be. Now, if we look at the middle of these rays, I can see that whoever drew that has been kind and that that middle ray is heading straight for the vertex of the mirror. So let's begin by extending this ray up so it meets the vertex, and we'll label up the angle of incidence as being theta. The reflected ray needs to make the same angle theta with the optical axis, and we can achieve that just by making the reflected ray and the incident ray symmetric about the optical axis. If we look at the incident ray, I can see it passes through this point here, which is 1, 2, 3, 4, 5, 6 squares above the optical axis. So therefore, we want the reflected ray to pass through the point that is 1, 2, 3, 4, 5, 6 squares below the optical axis when it gets that far from the mirror. So let's put our ruler so that it passes through the vertex and that point. So the reflected ray is going to look something kind of like that. Now we know that because this is a convex mirror, it's going to be producing a virtual image. So the backwards extension of this ray is going to be important. So while we've got our ruler in the correct spot, let's just draw on the backwards extension of this. And now label up the angle of reflection as being theta. Now we know because these three rays are parallel, they're going to be forming an image on the focal plane. To figure out where the focal plane is, well, we need to know where the focal point is. The focal point is going to be halfway between the center of curvature and the vertex. So let's figure out how far away the center of curvature is from the vertex. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 squares away from the vertex. So that means our focal point has to be 1, 2, 3, 4, 5, 6, 7 squares away. So it's going to be right here. So to represent the focal plane, we can draw on a vertical line which passes through the focal point. So I'm going to represent the focal plane by this line here. Now, of course, we know that the image has to be on the focal plane. And since we know that the backwards extensions to one of the rays intersects the focal plane here, that's where the image has to be. So we know that the image is right there. All we want to do now is complete the ray diagram so that the backwards extensions of all the reflected rays pass through that image. So if we extend this ray up to the mirror, then it's going to have to reflect. So its backwards extension passes through the image. So to draw on the reflected ray, we just need to arrange our ruler so that it passes through the point where the incident ray hits the mirror and also through the image. Here is the reflected ray, and here is its backwards extension. Doing the same thing for the last ray. Its backwards extension also has to pass through the image point. So the reflected ray looks like that, and its backwards extension also passes through the image. And we're done. We have located the image and drawn on all the reflected rays. Now, just one final thing. You see how this reflected ray here makes an angle of theta with the optical axis? Well, given that that is parallel to its backwards extension over here, that means that the backwards extension is going to make an angle of theta with the optical axis as well. Now, the distance from the vertex over to the focal point, we know that's, well, up to a negative sign equal to the focal length of the mirror. So what that means is that if you knew the angle that the incident rays made with the optical axis, and you knew the focal length, well, you could use probably trigonometry to figure out what the height of the image is going to be, or how far away it is from the optical axis. So that's just a couple of thoughts that might be useful to bear in mind when you're doing, say, a quiz.